Let's have a look at the international. It's just coming over the horizon here. And now let's zoom in on our biggest home away from home right now. It circles the Earth once every 90 minutes because it's orbiting at a speed of about 17,000 miles per hour, which is really fast. Imagine being able to go around the world once every 90 minutes. Here's the space station, currently occupied by, I think it's 6 space travelers from the US, the Soviet Union. Sometimes there are other visitors from the European Space Agency or from the Japanese Space Agency. And sometimes now they're even letting tourists on board, because there are some non-scientists, non-astronauts who are traveling to the space station and are scheduled to do so in the coming year. But there is made of a number of different modules, different parts that were launched at different times and then assembled in orbit like a great big, like a big Lego set or something. Those big wings are solar panels which provide power. They absorb collect energy from the sun and transform that into electricity to run the systems on board the space station. Again, this is the biggest thing ever built in space and is as far away from our planet as humans currently travel, our current home away from home. And sometimes you can even see it passing overhead. There are a number of websites, including one that NASA runs, that tell you exactly where the space station and when it'll be seen. So watch for that. And when it does pass overhead, it can be spectacularly bright, almost as bright as the planet Venus. Because again, it's really big and really low. So let's back off from the space station. Again, this is as far as humans currently travel from Earth, but we have traveled farther away from our planet than this. We'll leave the space station and Earth far behind to travel off to the farthest that humans have traveled from our planet. And that would be our satellite, the Moon, which we went to about 50 years ago. And to find the Moon, I'm going to back off a little bit farther so that when we look for the Moon, it's not going to be, we're not going to take a huge jump, I hope. Because I don't know where the Moon is right now. We will look around for it. Let me zero in and center on the Moon right now. Right there, at the end of that line, which is its orbit. So our satellite, the Moon, is our nearest natural neighbor in outer space. There are thousands of artificial satellites orbiting our planet, several thousand, but the Moon is our one natural neighbor. And right now we're looking at its dark face, not lit directly by the light of the sun, because it's almost between Earth and the sun, as you can see right there. One thing we can do, however, is turn off the nighttime side of the Moon so we can have a better look at its surface right there. Now, this is the familiar side of the Moon, the face that we are used to seeing, and we can notice the dark patches on the Moon's face right here. These dark patches were observed by early astronomers who thought they were bodies of water, so they called them Maria, seas and oceans. But they're not seas and oceans at all, but they were given very beautiful, almost poetic names. This big one here was called the Sea of Rains. This was the Sea of Tranquility. The Sea of Serenity. Here's the Sea of Tranquility, and the Sea of Nectar down here. The Sea of Islands is right down here below the Sea of Rains. And this really big one over here on the left side is called the Ocean of Storms. Beautiful, beautiful names. But if you look closely at the surface of the Moon, there are not just those dark areas. There are also light-colored areas, which are called the lunar highlands. And the highlands are where we see lots of craters. We'll zoom in close and have a look at some of those craters, which you can make out very easily right here, down here, and lots of them down here. Those craters were formed by the impacts of asteroids and comets in the Moon's past. And the seas and oceans are actually lava that bubbled up from beneath the crust about 1 billion years ago, covered over a lot of the heavily cratered areas, and as they spread out, and smooth and cooled, they form these dark areas, which are big flat plains of dried lava. So those are the differences between the light and dark colored areas on the moon. The Maria here are flat plains of lava, and since they formed, more recent craters have formed on top of them, more recent impacts formed by, again, the impacts of asteroids and comets. And then on the highlands, the lighter colored areas, that's where we see a lot of the older craters on the surface of the moon. And the moon does go through a cycle of phases, which a lot of people like to observe. And humans did travel to the moon 50 years ago to walk on its surface, collect about 800 pounds of rocks. And there are plans now to send humans back to the moon so that we can resume our studies of our nearest neighbor in outer space. We'll leave the moon farther behind and back away from it and the Earth. I'm going to add in the orbits of the other of the various objects orbiting the sun. So right there we can just make out the orbit of the moon around Earth, and here's the orbit line of the Earth itself. So as I back away even more, we'll be able to see the other orbits of the other planets in our solar system. Move to a higher angle of view so we can look down on those orbits. And as we do, and now we're talking about things that are so far away that measuring the distances to them starts to become really difficult. The moon is 250,000 miles away, about 240,000 miles. It took the Apollo astronauts about 4 days to cross that distance. Wow. However, something that travels even faster would be light or radio signals. They both travel at the same speed. Light travels 186,000 miles per second. And if you could travel as fast as light or as fast as radio signals, you could travel around the world 7 times in 1 second. And you could travel from Earth to the moon in 1.5 seconds. You could travel from the sun to the Earth in about 8.5 minutes. Now, we learned in school that that distance is 93 million miles, or 150 million kilometers. But astronomers say that it's 8.5 light minutes away, the length of time that it takes light to travel from the sun to the Earth. So another way of looking at that is that the light that you see when you look at the sun left it 8.5 minutes ago. So in a sense, when you go outside and glance up at the sun, you're seeing what the sun looked like 8.5 minutes ago. If you want to know what the sun looks like right now, you have to wait another 8.5 minutes for the light that's leading it right now to cross the 93 million miles to Earth to get to our eyes right here. So interesting idea about how far away things are in space and how long it takes light to get here from there. So as we travel farther off, we're going to see objects that are even farther away, of course. The sun, 8.5 light minutes. Some of the other planets are several light hours away. If we look at the most distant planet, the planet Neptune, way out here, that's about 4.5 light hours away from Earth. And that is the diameter, the radius of our solar system. Total diameter is about 8 light hours. So that's the scale of our solar system. And when we look at more distant objects, we'll see things that are just so far away. Trying to measure their distances in miles becomes kind of silly. Sort of like trying to measure the distance to the length of Golden Gate Park in millimeters. The number just gets so big, you really can't wrap your mind around it. But as we travel farther and farther out, we'll start to encounter objects that are light months or light years away. In some cases, hundreds or even thousands of light years away. Now, we talked about how far away humans have traveled from Earth. We have also sent spacecraft far out, but those spacecraft, which have been traveling for many, many years now, have not even been traveling for 1 light day. The distance that light would travel in 1 day, even though they've been traveling for 40 years or so. But the farthest evidence of humanity, the most distant evidence of humanity in space, is not in the form of a physical object, but rather in the form of radio signals from Earth. We've been broadcasting radio signals since for about the past century or so, And those radio signals have formed a giant bubble around our planet, which is about 100 light years in radius, which you can see right here. This is as far as our human presence has reached into space. But you'll see that this is only a very, very tiny part of our galaxy, let alone the rest of the universe. We'll talk a little bit more about this later on. But as we travel even farther away, we are now quite far away from our planet. Leaving our galaxy, we're moving directly away from the center of the galaxy. And now we see the galaxy take form as a very thin disk of stars. According to astronomers, the Milky Way galaxy is about 100,000 light years across, which means that a beam of light would take 100,000 years to cross the diameter of our galaxy. It's made up of several 100 billion stars, depending on which astronomer you talk to. Some used to say 100 billion. Now some say as many as 400 billion. And notice that there's our radio footprint, we are nowhere near the center of the galaxy. We're off about 2/3 of the way from the center. You can just see how thin the galaxy is. We're way off here to the side, on the trailing edge of one of the spiral arms that wraps around from the center. The Milky Way is not the only galaxy in space. About 100 years ago, astronomers discovered that there are other galaxies. In fact, we can see a couple of other galaxies right here, 2 other members of what's called the Local Group. That's the small cluster of galaxies to which the Milky Way belongs. And those are the other 2 large members of this small cluster. It's a group of about 20 or 30 galaxies. That's our own cluster, the Local Group. But there are other galaxies and other clusters. When astronomers discovered that the Milky Way is not the only galaxy in space, they also found out that the galaxies that we see are moving farther and farther apart from each other. They're moving away from each other. So not only was the universe bigger than they had thought, it was more than just one galaxy. It was lots of galaxies. But those galaxies are all moving apart. The universe is getting even bigger than they ever thought it was. So they found out that about 100 years ago, in the 1920s or so. And now that we've left the galaxy, we see all those spots on our dome overhead. Each one of those spots that we see is not a star, as it was when we were in the galaxy. Each one of those spots is another galaxy. And as we travel even farther off into space, we'll see that the galaxies do also come in clusters. The local group, our local cluster, is just one small cluster of galaxies. There are others which contain thousands of galaxies. And we can see clusters of clusters, or superclusters as they're called. And we can see that the universe has a texture. It has a sort of a foamy consistency almost. It looks a bit like a sponge, large voids between great clusters and strings of galaxies, as we can see here. And as we travel even farther out, we start to get an idea of the distribution of galaxies. Now, this observation right here, this image that we see, is again based on actual data. It's based on real observations, real information that astronomers have seen. And it shows that the distribution of galaxies that has been mapped so far looks rather interesting, like a giant bow tie, or maybe like a big butterfly. Is that the real shape of the universe? Well, no, not really. This empty area right here, the neck of the narrow part of the bow tie, is it's not empty space. That's just parts of the universe that we haven't mapped yet. So we don't have good information about those areas. We're pretty confident that there are lots of other galaxies, just like in this direction and this direction over here. We just aren't seeing them because there's stuff in our way, blocking our view. What is in our way? Well, what's in our way is the dust and gas in our own Milky Way galaxy. Remember, the Milky Way is a flat disk. When we see it in the sky from here on Earth, it looks like a band of light crossing the sky. But that band of light also contains lots of dust, which is blocking our view. And this is what's being blocked from our view, from our planet Earth, from our view on Earth. So, our map of the universe is still incomplete. This is not all the data that exists for us to look at. But as we travel even farther and farther out, we see many, many, many galaxies out there. Some say that there are hundreds of billions of galaxies. And the farthest things that have been detected so far are what are called quasars, those pale orange dots right at the edges of those great fans. Those are the centers of newborn galaxies. And those are the most distant objects that have been detected so far, some of them about 10 billion light years away. For them to be so bright, and they are extraordinarily bright, to be so bright that far away, they have to be extremely energetic. So astronomers believe that these are the cores of newborn galaxies in the process of formation. In 1948, some astronomers thought about what was discovered in 1921 and said, okay, we found out the galaxies are moving apart. The universe is expanding. When did that expansion begin? If we run time backwards, when do we think that expansion of the universe began? And they came out to a figure something like 13, 14 billion years. And a few did some calculations and figured out how hot the universe should be. If everything were all smushed together, how hot would it be? And after 13 billion years, to what temperature would it have cooled? They calculated that the temperature of the universe should have cooled down to about 3 degrees above absolute zero. 3 degrees above the coldest temperature possible. And in 1965, a couple of scientists were doing some experiments and measurements, and they detected this faint radiation coming from all directions, which came out to be this microwave radiation permeating everything, coming from every single direction. And they managed to take the temperature of this radiation, and they found that it was 3 degrees above absolute zero. So the prediction made way back in 1948 about what the temperature of the universe should be came true, or was found to be the fact. And so this is called the cosmic microwave background. It is a faint radiation that is the echo of what's called the Big Bang, and that is when the galaxies began to expand farther and farther apart from each other. And that is as far as we can see in space. This is basically a baby picture of the universe, only about 300,000 years after the expansion of the universe began. And since this is as far as we can go, we've got nowhere else to go but back in. And if it occurs to you that this map of the universe, this 3D model of the universe, makes it look like we're at the center of the entire universe, that's a very satisfying thought. It makes you feel really important. But that's only the product of the fact that we're the ones who made the map. It's based on our observations of things around us. I mean, if you look around you, sure, it seems you're at the middle of everything. But if someone else in another part of the universe made their own map of the universe, it would look somewhat similar with them at the very center. So we don't think we're really at the very, very center of the universe. There are lots and lots of more galaxies and clusters and superclusters and lots more to the universe than we see here. And not only that, I mean, speaking of which, about there being more to the universe, I mean, that map of our universe was, again, incomplete. But even if it were, astronomers say that there's more to the universe than just what we can see, because the movement of the galaxies that we can see right now cannot be accounted for by the amount of mass that is observed. There's a lot more to the universe than just what we can see in our telescopes. And what we see amounts to what astronomers have calculated is only about 5% of the universe. So we're only seeing a tiny, tiny part of the entire universe. We're coming back in toward our neck of the woods, our part of the galaxy in one of the spiral arms. There's our radiosphere, our radio bubble. We do want to mention something else too. One more mind-boggling fact, and the universe is really just one mind-boggling thing after another. We often wonder, are there other planets? Are there other solar systems? Well, certainly there are. And here is a map of some of the extrasolar planets that have been detected since 1994. Each one of those little circles that you see there is a planet orbiting another star. And to date, astronomers have detected about 4,100. And they're always adding to that. There are more than that now. And notice that within this radiosphere, within this radio bubble of ours, there are some of these exoplanets. Now, if any of those planets have the right conditions for life, well, that's an interesting thought. If they are technological civilizations living there, they might have heard our radio signals by now because they're inside our radio bubble. They're within reach of our radio signals. Any civilizations that are just outside the radiosphere have not picked up our radio waves yet. They wouldn't know about us. So that's an interesting thought. But 4,100 known exoplanets, and the number is growing constantly. As we consider that, the number of other planets, how many of them are like Earth? We don't know, really. I mean, some are rocky, some are just the right distance from their star for liquid water to exist. But what about their compositions? What about their atmospheres? What about other conditions that require life? We don't know too much about those other planets and whether or not they could harbor life. So as we approach our own star and its family of planets, we find that as far as we know, so far, there is only one planet that satisfies all the conditions for life. It's the right composition. It has the right amount of water on its surface. It has the right combination of elements to create the nutrient environment that we need for life to exist. It's just the right distance from its star, so it's neither too hot nor too cold. And so our own planet Earth is the one place that satisfies all those requirements. And out of all the billions of galaxies and billions of stars and the thousands of other planets that we know about, we truly find that there is no place like home. So as we return home to the planet Earth, we welcome you back to the one place that has life, the one place that it turns out is really a fragile place, one that we should do everything we can to preserve and protect. And that's our own world, our own home. So, thank you all very much. Welcome back to Earth, and we hope you've enjoyed this tour of the universe.